Welcome back. Now we move to the last chapter of this course about the inverse function theorem and the implicit function theorem. There will be 3 sections in this chapter. In this video, I'm going to cover the first section, which is a general introduction to the problematic of this chapter that actually I mentioned in the introduction to the course. So there are 2 related and interesting problems. The first one concerns inverting a function, or in simple terms, if we have an equation of the form y equal f of x, can we write x equal g of y? You encountered already this problem at school, and you know that this is possible only if f is bijective. But the question now is, if y depends smoothly on x, does x depend smoothly on y? Or otherwise stated, if f is smooth, meaning that it possesses enough derivative, does it follow that f minus 1 is also smooth? In general, the answer is no. So we have to put some extra assumptions. So here's an example. Just consider the polynomial x cubed. It's bijective. It's differentiable. It's actually as smooth as it's c infinity. But the inverse, which is given by the cubic radical, is not smooth because the problem is at 0, of course. Okay, so it's continuous. It's a homomorphism actually, but the inverse is not smooth. Okay. So, however, under certain assumptions, the answer is yes, and this is what we shall deal with in this chapter in full generality. Okay, in the context of Banach spaces. Okay, now those among you who love topology will ask a similar question, or a little bit simpler. If y depends continuously on x, does x depend continuously on y? Okay, so if f is a continuous bijection, does it follow that the inverse is continuous? Here again, the answer in general is no, and we gave several counterexamples in the topology course. However, there are many interesting cases where the answer is yes. A continuous bijection whose inverse is continuous is called, as you know, a homomorphism. Homomorphism, as you know, is a central concept in topology. It's like the concept of isomorphism in algebra. So a homomorphism is a bijection that conserves the topological structure. So I mentioned the first example, we mentioned it in chapter 1. But we didn't prove it because it's a little bit hard. We'll prove it next year. If L is a linear continuous bijection between 2 Banach spaces, then its inverse is automatically continuous. Okay, and this is it's not trivial. Okay, this is called the Banach isomorphism theorem or the bounded inverse theorem. Second example that we encountered in the topology course, a continuous bijection between 2 compact topological spaces where the image is Hausdorff, then the inverse is necessarily continuous. Okay. Here actually we know that first of all y must be compact because the direct image of a compact set must be compact, and the fact that y is Hausdorff also implies that x is also Hausdorff because the Hausdorff condition is topological property. Okay. This is very easy actually to prove. So just prove that F maps closed sets into closed sets. The third example is that a continuous bijection from R to R is a homomorphism. So here again, the continuity of the inverse is automatic. This is not terribly difficult to prove. It requires some time. So you can do it if you like. However, there is a deeper theorem that states that a continuous bijection from Rn to Rn is a homomorphism. Okay, and all the proofs that I know of this theorem requires advanced tools from topology. Okay, so that's a deep problem. Actually, you can formulate several equivalent conditions to the continuity of the inverse. Like, for example, F is closed, F is open, F map, the inverse image of a compact set is a compact set, and so on. Or the fact that the inverse image of a bounded set is a bounded set, or that f of x tends to infinity as x tends to infinity. But you cannot easily prove any one of these equivalence things. So you need a new tools. Okay, so second problem that we mentioned in the introduction is about the implicit function theorem. If two variables x and y are related by an equation of the form f of x y equals 0, can we express y as a function of x or vice versa? Here again, without any additional assumption, the answer is no. For example, even in the simplest case of an equation of the form x squared plus y squared minus 1 equals 0, which is the equation of the circle, we cannot solve y as a function of in terms of x or vice versa, because the circle is not the graph of a function. However, small part of the circles are, as you know, graphs of a function. So for example, if you restrict x and y to a neighborhood of the North Pole, then y is positive, and therefore we know that y is necessarily radical of 1 minus x squared. Also, if x and y vary in a neighborhood of the South Pole, then y is necessarily minus radical of 1 minus x squared. However, no matter how close to the East Pole 1, 0, we cannot solve y in terms of x. This is impossible. But we can solve x in terms of y. Okay. Because around the East Pole, the part of the circle around the East Pole is not the graph of a function. Y cannot be a function of x, okay? Because we have, for the same value of x, we get two values of y, one positive and one negative. Okay, and similarly for the West Pole. Okay, but the second question is, suppose that, so we cannot hope for a general solution, but we can hope for a local solution. So suppose that we can solve the equation f of x equal y locally and write y equal g of x. If f is smooth, does it follow that g is smooth? This is an important question, because unlike the simple example, here g, for example, was radical of 1 minus x squared or minus, though we had simple formula for g, but in general there is no simple formula for such map g. This is why we are interested in knowing the properties of g without actually having a formula for it. So we ask if g is smooth. This is the question. Okay, so as a warm-up, before we tackle the problem in full generality, let us see what happens in dimension 1 from R to R. Okay, so consider a map from an open subset of R to an open subset of R, which is smooth and bijective. Okay, if the inverse is differentiable, then necessarily the derivative never vanishes. So this is V, not I. Conversely, if f prime never vanishes and f minus 1 is continuous, then the inverse f minus 1 is as smooth and f. And this is very easy to prove. This is what we shall do. And the arguments are very simple. So it's better to present the argument in the simplest setting before we move to the more general context of Banach spaces, where the ideas may be a little bit obscure. So suppose first that f minus 1 is differentiable. Then, by definition, f minus 1 of f of x is x. So, and I know that f is differentiable and f minus 1 is differentiable. So, by the chain rule, so if I differentiate this side, I get f minus 1 prime of f of x times f prime of x, and the derivative of x is just 1. So this means that f prime of x cannot be 0. If it's 0, then I will get 0 equal 1. Okay, so this is the easy part. And therefore, it's not 0. And I have a formula for the derivative of the inverse. The derivative of the inverse is simply the inverse of the derivative. Okay, very easy. Or if you like, f minus 1 prime of y is 1 over f prime of f minus 1 of y, if you like it in this way. or if you like, f prime minus 1 of y is 1 over f prime of x. Okay, this is very easy to remember because formally we can write dx over dy as 1 over dy over dx. Okay, but this, yeah. Now I'm interested in the inverse, actually, in the converse. So this is what a physicist would write, but it assumes that the derivative does not vanish. Okay. Now, suppose that conversely, f minus 1 is continuous and f prime never vanishes. Okay, it's an assumption here. We'll prove that f minus 1 is differentiable by going back to the definition. Okay, so we pick a point B in the target set, and we write f minus 1 of y minus f1 of b over y minus b. So here, we just take y equal f of x because it's a bijection, and b equal f of a. So I write this as x minus a over f of x minus f of a, and this is 1 over this Newton's ratio. Now here we have to be a little bit careful. We have to use the continuity of f minus 1 because otherwise things may be wrong. I know that this ratio tends to the derivative as x tends to a. But how do I know that as y tends to b, x tends to a? This is just continuity of f minus 1. Okay, so continuity of f minus 1 implies that x minus a is small if y minus b is small. Therefore, when I let y tend to b, this ratio tends to 1 over f prime of a or 1 over f prime of f minus 1 of b. Okay, so this means that f minus 1 is differentiable and its derivative is given by this formula. Necessary, must be, there's no other way. Okay, now if f is of class C1, what can I say about f minus 1? It's also of class C1. Why? Because if f is class C1, then f prime is continuous. And the inverse function 1 over t is continuous on R without 0. So we can write actually f minus 1 prime as a composition of 3 maps. F minus 1, which is continuous by assumption, f prime, which is continuous, and the inverse. So the composition of 3 continuous functions is continuous. So then f minus 1 prime is continuous. And now, by induction, we prove that if f is of class Cn, then necessarily f minus 1 is of class Cn. Why? We prove this for n equal 1. Suppose that it's true for n minus 1. And suppose that f is of class Cn. Then, as you know from the last chapter, this means that f prime is of class Cn minus 1. So, by the induction assumption, f minus 1 is of class Cn minus 1. And again, by using the composition of 3 maps, we see that f minus 1 prime is the composition of 3 maps of class Cn minus 1. So it's itself of class Cn minus 1. So f minus 1 prime is of class Cn minus 1. And this means that f minus 1 is of class Cn. Okay. Now, the assumption that f prime does not vanish is a strong assumption. What if you just know that f prime does not vanish at one point, okay, which is easier to deal with? If f prime is continuous, then f prime does not vanish on a neighborhood of that point. And so we can apply the previous discussion, and we see that locally around the point A, f minus 1 is as smooth as f. But actually, we can prove a better result, actually. If we don't know that f is a bijection, okay, this is the difference between. So just so far here we are assuming that f was a bijection. But if we don't know that f is a bijection, but we know that f prime is continuous and does not vanish at a point, then actually we'll prove in a general context that f is bijective near the point and its inverse will be necessarily as smooth as f. Okay, and this is the content essentially of the inverse function theorem or the local inversion theorem. Okay, so it's easy to state. And now, what is the analog condition of f prime does not vanish. In general, f prime of a is not a number. It's a linear bounded map. So the condition that f prime of a does not vanish is the condition that f prime of a is an isomorphism. Or if you like, if you are working with a function from Rn to Rn, this means that the Jacobian matrix is invertible. Okay, so this will be the key to generalize the inverse function theorem to Banach spaces. Okay, and everything will just be the same. Now, what about problem 2? Let us say some word about it in one dimension. So just two real variables, f of xy, related by an equation of the form f of xy equals 0. And suppose that we have one solution of this equation. So f of ab is 0. We will prove that if f is smooth and the partial derivative of f with respect to the second variable does not vanish at the point ab, then we can solve locally this equation. So there exists a smooth map G defined on a neighborhood of A that solves the equation. Okay. And now, if you consider this equation, which is true on a neighborhood of A, if a function is identically 0 on a neighborhood of the point, then the derivative is 0, as you know. So, but what is the derivative of this function of one variable? If you call it psi or h, if you call this h of x, what is h prime of x? The chain rules tell me that, you know from first year actually, that the derivative with respect to x of this function is the partial derivative of f with respect to the first variable times the derivative of x with respect to x, which is 1, plus the derivative of f with respect to the second variable times the derivative of the second argument, which is g prime of x. This is the chain rule that you know. Of course, everything is evaluated at the point x g of x. And since this is so, in particular, if here I have just to evaluate it at AB, because I just know that the derivative does not vanish at AB. So I can divide by this derivative, and I get g prime of x is just the inverse of this map times. So the inverse of the second derivative with respect times the derivative of the first derivative. Okay, so sorry, there's a slight imprecision here. This equation here is true for, so I evaluate f at x g of x. But here I evaluate them at AB. Okay, because I know that this is not 0. Okay, and or if you like, you can assume that the partial derivative of y at any xy in the neighborhood of xy does not vanish. But this is true actually if the f is smooth enough, and the partial derivative does not vanish at the point, then it does not vanish on a neighborhood of that point. So this, you probably encountered this in first year, and this formula is called implicit differentiation. Okay, this is how it's very easy. Okay, so this is essentially the content of the implicit function theorem in dimension 1. So we'll generalize this, but as you know, instead of numbers, we are going to deal with operators, so with linear bounded operators. Okay, now just some remarks before we move to the next section. Except in the first lemma in the next video, we need to work in complete spaces for 3 reasons. First, we will need to use the Banach fixed point theorem that I will recall now. Second, we need the fact that the set of isomorphisms between two Banach spaces is open. We need this fact, and this is a necessary condition for defining the inverse map from the set of isomorphism between two Banach spaces into the set of isomorphisms between. So this map given by S-1 is of class C infinity, as you know, but this requires that this domain of definition of phi. This requires that the domain of definition must be open, okay? Because we define differentiability of a map on an open set, and we know why we need this. We don't know what does it mean for f to be differentiable on a set which is not open. There are several ways to overcome this, but so far we need to work on an open set. So This is why we need to work between Banach spaces. Okay, in most of the results of the previous chapters, we didn't need this assumption. Okay, but now we need it. So let us recall the Banach fixed point theorem or Banach contraction principle that we studied in second year. If we have a complete metric space and a contraction from the space X to itself, contraction means it's Lipschitz continuous with constant less than 1. Okay, we can call it K contraction if you like. Then this map has a unique fixed point. Okay, fixed point means that psi of L equal L. We proved that in second year, and there is a constructive algorithm for finding the fixed point. Just so simple actually. We start with an arbitrary point x0 and we iterate the map psi. So x1 equal psi of x0, x2 is equal to psi of x1, and so on. And then the condition of contraction tells me that xn is a Cauchy sequence. And the completeness assumptions implies that xn has a limit L, and then it's easy to prove that L is the required fixed point. Okay, so this is where completeness comes into play. Now, two other remarks. First, the assumption that psi maps the space into itself is essential. First of all, if psi of x equal to x, then x and psi of x must belong to the same space. Okay, so this is why the source space should be equal to the target space. But even if we work more generally, if x is a subset of a bigger space y, and psi maps x into y, and it's also a contraction, then psi need not have a fixed point. Okay, here's an example. Consider the function psi from the interval 0, 1 to the bigger interval 0, radical 2. Okay, both equipped to the usual distance. And psi of x is just radical of 1 plus x squared. So, of course, psi maps 0, 1 into 0 radical 2 because this is bigger or equal than 0. And if x is less than 1, then x squared is less than 1. So this is less than 2. So it maps this interval into this interval, but it has no fixed point, as you may easily check. Okay. What is the problem? The problem is that the target space is not equal to the source space. And of course, a contraction cannot possess more than one fixed point, as you may easily check. If you go back to the definition, if psi has two fixed points, x and y, then we'll get the distance between x and y less than k times the distance between x and y. And since k is less than 1 strictly, then dxy should be 0, and therefore x equal to y. Okay? So we cannot give a counterexample with more than one fixed point. Okay, and also, second remark is that completeness is essential. Okay, so, and we know where we used it actually. And here's a counterexample. If you consider just the set of rational numbers between 1 and 2, and you equip it with the usual distance, and you consider the map given by x over 2 plus 1 over x. Okay, now, of course, this psi maps x into itself, as you may easily check, because if x is rational, then psi of x is rational, and if x is between 1 and 2, then psi of x is between 1 and 2. So we have a self map, and you may check that it's a contraction, but it has no fixed point. Why? Because the fixed point here is radical 2. Actually, there are two fixed points, radical 2 and minus radical 2, but they don't belong to the space. Okay, so if we don't know r, then the fixed point does not exist. Okay. So this completes this small introduction. Thank you for attention, and see you next time.